This content is brought to you by BEC Financial Technologies, developing and operating IT for Danish banks.
Please warmly welcome Grzegorz.
We have only 30 minutes, but my job for today will be to get us all on the same page regarding distributed systems and fundamental constraints that basically serve as those main architectural drivers behind our choices. I believe this is a very important topic because our industry has been going in circles, and I've seen loads of architectural evolutions that went into the world of distributed systems prematurely, and they went really bad because people were either not aware or ignoring some of the basic constraints that should influence the decision process since the first minute of the decision making. My name is Grzegorz Piwowarek, and I am an independent specialist working mostly with architecture and distributed systems. Yes, I'm a Java champion, but I usually tend to pick just one of the tools I use. I tend to go for the tool that makes the most sense for the job. But in this case, we are working with stuff that's universal. It doesn't matter if you are using COBOL, JavaScript, Java, AI, no AI. Fundamental constraints of physics apply anyway. So I remember it was around, I think, 2010, 2009, when the microservice revolution started. And it was pretty interesting because you could find even companies putting, microservices and one of the perks on their job ads. And from my personal experience, it looks like they went totally over the top with that. The problem is that microservices is not a bad architecture. It's a pretty good one. However, the problem is that if you take a good idea and apply it in the wrong context, well, it makes it a bad idea. And sometimes good ideas also have costs associated with them. So if you are trying to apply that very good pattern for your really tiny use case, you might still end up paying more the cost than experiencing benefits from that. And the funny thing is that microservices is not the first time we invented similar architectures. In the past, we had something called SOA, service-oriented architecture. And if you try to dig deeper into that and figure out what the difference was, it's really hard to tell. Some people will tell you, oh, SOA, there were like XMLs flying around, we had service buses, and now we have microservices. People say, okay, you have Kafka and REST endpoints, but the core idea was the same. Just slice your system into smaller pieces, divide and conquer, and get something out of that. And I believe many companies went into this way too early. In my consulting experience, I worked with companies that had 6 people working on 150 services, having just one non-paying customer on production. And well, guess how it went. Usually they end up just paying more cost than experiencing benefits of that great architectural pattern. So my job for today is to recall the fundamental physical constraints that should influence our choices. And we'll start with the most obvious one, which is a CAP theorem, which is the most important constraint that probably most of you already heard about. And if you simplify that, it's one of those pick 2 out of 3. So there is consistency, availability, and partition tolerance. And consistency is that property that makes your system behave like a single node, single threaded system, despite the fact that there are millions of nodes. They are disconnecting, connecting, appearing, disappearing, but still the whole system behaves as one, even single threaded. So you might have thousands of clients writing to different nodes, but if your system behaves, it'll appear as if it was just a single node, Well, that's the consistency. This is very cool property to have in your distributed systems. But there's another cool one, availability, which is defined as an ability to answer with a non-error response whenever you want to. So imagine a node. You send a request there. And now you can either not answer at all, or you can answer with potentially outdated answers. That's one of the fundamental trade-offs. If you are able to answer always at any point, that's availability. But if you need to wait some undefined period of time to be able to answer, your system is no longer available. And guess what? There is the third property, which is pretty cool, and that's partition tolerance. That means basically that even if we cut all the cords between all those thousands of nodes, and if the system operates normally, that's the partition tolerance. A pretty cool one to have. So now, before we dive deeper, let's answer one very fundamental question. What's the core property of distributed systems? If you look up a definition from Wikipedia, you will probably read something about multiple components, nodes working together to achieve some similar goal. Yeah, that's true. But there is one very important property that makes distributed systems hard. And that's basically communication over unreliable channels. So if we had a distributed system with 100% reliability guarantees, we would be dealing with all of those problems because we would never experience partition tolerance. And there are such systems, like your multi-CPU systems are basically distributed systems working, communicating over reliable channels. And suddenly you don't need to worry. Your CPUs don't need to choose between consistency and availability because guess what? Because your channel is reliable. But with networks, many things can happen. Networks are kind of by design unreliable. Those can drop packets, sometimes packets can order with huge delays, they can come up unordered. Many weird stuff can happen. Even weirder stuff. Sometimes this is actual video footage, I believe, from Google. They figured out that apparently those cables that are lying underneath oceans, the magnetic fields somehow they draw sharks into them. So even stuff like this can happen. People over years experimented with different mediums to transport those packets, but unfortunately others turned out to be lossy as well. So yeah, this is a Wikipedia page for IP over avian carriers. So at the beginning, I told you that the fundamental constraint is pick 2 out of 3. But the catch is, with distributed systems working over classical network, you always need to be ready to handle partition. You always need to have partition tolerance because, well, your packets can drop. So the reality is that you need to always pick either C or A because P will always be there. And that makes things complicated because let's say you have 2 nodes, just like on the animation on the screen. Node A is carrying some value, node B is carrying some value. As long as there is communication between them, not an issue. They can always agree on the same value and act just like one entity. However, when partitioning comes and we cut the cord between them, now those nodes need to make a choice. They can either stay consistent and say, I don't know what's the newest value, I can't give you an answer, or they can stay available and answer with the last value they remember, which can be outdated. This is essentially the CAP theorem distilled. So now, we are sending messages over unreliable channels. So let's figure out a simple algorithm how to guarantee delivery. Well, we have unreliable channels, but we can have delivery guarantees. For example, TCP/IP is a great example of that. So let's say we are trying to communicate over, let's say, a Google Meet call. And how do we structure our communication to make sure that the second side receive the message? Well, we can agree that if the second part, if this person you are on a call with, they receive your message, well, they can wave, for example, or something. And if you observe that second person waving, well, it's pretty clear that the person received the message. But what if they don't wave back? The most reasonable thing to do is to, well, resend the message and keep resending this message forever until they eventually wave back. And this gives you guarantees that at some point, maybe in a minute, day, year, millennium, at some point they will get this message, an act of retrying forever. But as you can guess, it can take some time. Let's expand this a bit. So let's say we have a case where it's just two sides that want to coordinate. So it's not just us trying to get an ACK from the other side to ensure delivery guarantees. Let's say there's just two of us, and we are trying to coordinate. Let's say we are generals and we are trying to attack a city. And we can communicate only by using messengers. So the trick is, we want to attack both or none of us. So how can we make this happen? We are sending messengers over the battlefield, but guess what? Sometimes they get captured. So I'm sending one messenger. They get the message delivered to the other general. They come back. And well, if they came back, that means they got the message. But do they know that I got the message, that they got it already? Not really. So technically, I should also send another messenger confirming them that they got the message. What if that messenger gets captured and never arrives? It's not that easy, as you can see, because this could keep going forever. So we should be just sending ACKs forever. And there is no solution to that. There is no deterministic ways for two parties to coordinate over an unreliable communication channel. So if there is a chance that the message might be dropped, well, here's a problem. The problem is that retrying forever is not always safe as well. If we are retrying a message or an action that sets user status to active, that's an easy thing, because if you make that user active over and over again, you always get the same result back. But if you are trying to increment a counter, well, guess what? If you are retrying that action multiple times, the result is different, because the counter keeps on going. This is why idempotency is so damn important, because in the world of distributed systems, if you want to have some delivery guarantees, you will be retrying a lot. Things will be failing, and you will need to retry, unless you don't care about delivery guarantees. So this simple property, well, I'm sure you've heard about that, but it's super important whenever you want to have some delivery guarantees, because you will be retrying a lot. And network retries might cause duplicate requests. Actually, I witnessed quite a serious production issues causing a double trade booking recently with one of my customers recently. What happened is that it turned out their HTTP client was tuned to retry requests on network errors. And what happened is they were very unfortunate, because that network request was triggering a huge trade booking, and that happened precisely when the instance was going down during the rolling upgrade. Not fun. The same can happen with load balancers and basically anything along the stack. And idempotency is that stuff that prevents unwanted side effects. So you can hear, obviously, companies saying they are providing you tools, providing you exactly once delivery guarantees, but it always comes with an asterisk. There's always some small text written somewhere in there, because exactly once is simply not possible, because this is how physics work. In order to be able to provide exactly once delivery guarantees, you would need to have a request travel to someone, and you would need to have guarantees that ACK can travel back to you. But anywhere along the way, something can be dropped, so you always need to retry. So the reality is, you need to make a very difficult decision, because you can have either at most once or at least once delivery guarantees. At most once means that we are sending a request, forgetting about it, and, well, it either arrives or not. Hence 0 or 1 at most once. And at least once, well, if you want to have this delivery guarantees that is received at least once, well, you need to deal with duplicates. You need to be able to deduplicate, and idempotency is super important for that. And this is why you can achieve effectively exactly once. But that means you need to have at least once with idempotency on. That's probably as close as it gets to having exactly once delivery guarantees. However, so you did slice your system into 100 separate nodes, and now you want to have absolute delivery guarantees of anything in there. So you'd be probably just retrying a lot. And that's problematic, because there's this phenomenon of temporal coupling. So if your system suddenly consists of 1,000 nodes and they all need to be up and running at the same time, to give you the illusion of this strict consistency, now we have a problem. Because if you want to be strictly consistent, all those nodes need to be able to answer at the same time and timely. If not, well, you don't have availability and you are not able to respond, and your system might act like it's not online. But guess what? That communication between nodes, it takes a lot of time. So when it comes to cap theorem, that's probably you've heard about, but there's a problem with that. It focuses mostly on what happens when something goes wrong. So when there is a partitioning, well, you need to choose C or A. Okay, but what do we do when there is everything okay? There is no network partitioning, the network works. What do we do then? And this theorem is actually an extension of that and very valid. So obviously, if there's a partitioning, you need to go for availability and consistency. But whenever everything is okay, you need to choose either latency or consistency. Because if you always want to stay strictly consistent, it will cause you latency. All your nodes retrying forever, trying to communicate, agree on the single version of a value, it takes a lot of time. And if this takes too much time, it's almost as bad as, well, the system going effectively down. So that's another thing that's worth considering, because quite often we don't want to have, well, at first it sounds like we would like to have fully strictly consistent systems. But if you start looking at the fundamental constraints, suddenly it's not really a viable option to have a huge system always behave as if it was just a single one. So a maybe more real life, well, almost real life example. Imagine you are checking in for a flight. And now you have a couple of options. You have a couple of check-in desks. And imagine, let's say they are doing this the old school way without a real computer system. And they're doing this on paper. So now imagine what would need to happen, how much slow would the process get if they all would need to coordinate and talk before checking someone in. That takes a lot of time. But you could speed things up by, for example, applying certain ideas. Like, for example, every check-in desk could have a pre-reserved batch of seats that they can allocate. So at the same time, you could figure out a solution how to minimize the downsides of the distributed system you are working with. And that's the reality. The reality is that those constraints are in place, but they are not always problematic, because once you understand the domain, you should be able to figure out places where you can loosen up those consistency boundaries, because maybe that's not a problem at all. If you're building a core of the banking system, well, that's probably where you want to be strictly consistent. But some monthly reports, Well, if they don't appear immediately 1 nanosecond after midnight, but 10 milliseconds, that's probably okay. So this is another thing, a very important one to add. It's not like we are always true. When we say we don't want to have a strictly consistent system, it's not like we are accepting the fact the system will be inconsistent forever. You don't need to choose one of those two, because the reality is that consistency is a spectrum. That consistency in CAP, strict consistency, a single unit illusion, that's the strong consistency. And this assumes that data converges immediately. However, on the other side of the spectrum, there is this accidental consistency or permanent inconsistency. And this is basically a system that doesn't guarantee you anything. So the data converges, well, maybe, or maybe not at all. However, if you look up various vendors, they came up with multiple various levels of guarantees for consistency, somewhere in between those. However, the one that we have time to speak about is eventual consistency. This is a very pragmatic one, where you trade off a bit of consistency, but you still get guarantees that your data converges eventually. Maybe in 10 milliseconds, maybe in a second, maybe in a minute, but your system guarantees that this data converges and you can trust it. So if we loosen up that strict consistency for eventual consistency, that's where we can get an availability and speed. Basically the cost of a temporary disagreement, which quite often won't be a problem. Because, for example, if your reporting data refreshes not immediately, but after 100 milliseconds, that's probably good enough. So while networks are slow and unreliable, and we can avoid having everyone to agree on everything, this slows us a lot and makes our systems behave, makes our system that strive to be strictly consistent behave as if they were simply not available. So let's take a very simple pattern, how we can achieve that. So we have communication between two services, service 1, service 2, and we want to get some data from the service 2. In the classic synchronous communication, we will, for example, call, issue an HTTP GET, wait for the response, and here we go. That's how synchronous communication looks like. But in order to go eventually consistent, we could adopt asynchronous communication. But don't mix it up. Sometimes people assume they can take this HTTP GET, throw into another thread and run it asynchronously. That's not an asynchronous communication. That's still synchronous communication done, well, asynchronously from another thread. In order to adopt asynchronous communication, what we need to do is totally change or to redo this arrow between them. So instead of service 1 asking service 2 for data, we could have the service 2 inform service 1 about the change that happened. And this is very important because now, instead of asking service 2 about data, data is being provided to you continuously. So whenever a change happens, there is an event traveling from service 2 to service 1. However, that travel can obviously take some time. Hence the eventual consistency, because now service 1 can use this data to, for example, to introduce some redundancy, build a redundant model of data, create a local projection that will make it independent from the service 2. So, for example, if you depended on some user data coming from the other service, now you can build it locally. And now use this data to serve your request. So even if the second service dies and is not available, you can still answer, you can still provide your service without waiting for the other service to come back. And this is a super powerful pattern. However, as you can get, it's pretty expensive to implement because suddenly you need to invest into eventing, build some redundant data models, and so on and so on. And by the way, if you are reacting to events, it doesn't mean you need to immediately have, Kafka or RabbitMQ. This can be done even with HTTP. But the difference is that service number 2 is sending an information to service number 1 in the form of more or less a webhook. So every local event, every service can build a local read model which can be optimized for their particular use case. This could be, well, a simple memory data structure, could be dedicated distributed cache, could be just another Postgres table. And suddenly you are independent. You don't need to talk to other services. You don't need to wait for them to come up. And it will be much faster because the data is right at hand. However, it's very easy to mess it up because eventual consistency is not the same as accidental consistency. And this is a pattern that I see all the time. And this is, you can consider this a consulting free money glitch. I've seen this everywhere, and this is very easy to spot you don't always need to fix it, but most people are not aware of that. So imagine you have a user service where you are creating a new user, and that service is persisting that user information in a Postgres table, and someone adopted asynchronous communication. They also need to send a message over Kafka or whatever else to other services. And this is the tricky part, because suddenly, for this to make sense, we need to have atomicity guarantees. We want the DB entry and event get emitted both or none, right? If we add an entry to a database and we skip an event, essentially the whole system relying on those events and building local projections will be broken. It will be even worse if we do it the other way around. If we send an event and we don't have an entry in the database, because from an entry in the database, we can recover somehow and emit an event later. But if the event was already sent and there is no entry in a database, well, that's your permanent inconsistency. And what I keep seeing all the time, especially with Spring and Hibernate, imagine you have this method called createUser, which is handling the createUser command. It's persisting entry into a database and then sending an event over a wire. So let's go one by one. So we are opening a transaction, persisting a user, then trying to send it over Kafka. So we send a request for a Kafka client to Kafka. Kafka received the message and has already committed it to a log, and then it's sending ACK back to the Kafka client. And that's where you drop a network packet. So in Java, you end up with an IO exception. And if you have an IO exception, it gets picked up by the transactional annotation. And well, if something went wrong, it means it's time to roll back. So we are rolling back the entry from a database, but the event is already sent through Kafka. So suddenly your whole system is now in a permanently inconsistent state, and this user is not even there. So this is a classic issue of a dual write, essentially a simple form of distributed transaction, where we are writing to two systems at once. And the solution is actually pretty easy. Oh, some of you that's been around longer, you are probably immediately triggered with ideas like two-phase commit, which would work almost. The problem is you can't really unsend a message through Kafka. However, the easiest possible solution is to convert that small distributed transaction into a series of small transactions. So you could write to a DB first and have an async process that picks up the data from a database and sends it over directly to Kafka asynchronously. And those keywords that you are looking after here, it's transactional outbox pattern and change data capture. And the idea is really very, very simple. So you write something to a database, you write something to a dedicated table, which is acting as an outbox, mimicking the event structure, and then you need to just simply pick it up using a separate process. So the easiest, the most trivial implementation of that could look like that. You're in a loop, polling from a database, trying to send it, and once you manage to send it, well, then you mark it as published. Done. Obviously, this can fail numerous times. That's why we would be polling over until we successfully manage to mark it as published. We can obviously generate quite many duplicates along the way. But you already know what to do about that. If you want to get smarter about that, there's the concept of change data capture. Change data capture using a while loop, it's okay. Technically, you can say it's a data capture, but there's a smarter way. So you have tools like Debezium that's able to, for example, plug in directly into Postgres replication system and take events right from there. So usually, if you're looking for a full-blown production solution, that's the ultimate combo, Outbox pattern and CDC. But obviously, this is a lot of extra complexity and a lot of extra work to make that happen. You know what would be easier to do instead? A monolith. So that's the problem, right? You can get those distributed systems to work. Those are great patterns if you have problems that can be addressed using them. If not, you're likely to juggle all of that extra complexity for really not a good reason. And this is a really short 30-minute presentations. We didn't really talk about distributed transactions, time synchronization, clocks in distributed system, leader election, locking, back pressure, versioning, and so many things. Distributed systems are hard, and you should keep that in mind since the very beginning. Because I believe at the moment that the best thing you can do, especially if you're starting from scratch in a small company, defer the decision to distribute as long as you can. But again, I don't know your context. It's possible that there is 100 people in the room and you're working with over 100 different projects. So remember that common sense is the ultimate best practice. But I feel like in the world of microservices and distributed systems, we kind of did forget about that. So thank you very much. My name is Grzegorz Piwowarek, and I hope you learned something.
Yeah, who would like to start the conversation? Oh, we have first person.
Hello. I would like to ask you about the scenario with reading data from another service. And you said that the second service should emit an event. Let's assume for a moment that we cannot control the service number 2, and as a result, we cannot expect them to send us an event. What do you think about case that service number 1 in some schedule try to get the newest version of data to refresh our local read model?
Okay, so this is quite a common pattern. So imagine you're, for example, integrating with a third party. Let's say you're integrating with, just any third-party provider of some service, and they might not want to integrate with you using Kafka. It's not like common to tell them, okay, you call Uber, like the Uber headquarters, and tell, okay, guys, we are integrating with you. It's our Kafka topic. Please send some events to us. No, that's not going to work. So some third-party providers will actually give you webhooks or some stuff to actually deliver events to you. If they don't do that, if you really want to, you can kind of mimic that. And usually you would do that by introducing extra service that's doing the polling on their own. So you would poll data periodically from a service using synchronous communication, and you could either use this data directly to refresh your local read model, or basically emit your own internal events from that. This is obviously doable, but not ideal. But sometimes makes sense.
Hi, great presentation, by the way. So I have a question about what you said about unsending a message. Yeah, this is true. I totally get it. But at the same time, you can send something like compensation message. So here you had a message, user created event. So you can send another one during this rollback that will be delete this user, and the state at the end will be the same. But still, I really value output pattern, so I know it. But what do you think about this sending these compensation messages?
Okay, so I don't know if you heard that, but the idea is that basically you can unsend a message by sending a compensating message. That's obviously true. The problem is that now you have two choices. You can either prepare all the consumers of that Kafka topic to actually understand compensating events, or you can solve this at the infrastructural level. So that's basically a trade-off. So yes, this could work, but the other option is probably more robust and easier to maintain long-term.
Thank you so much. And now it's time for your award.